So here we are discussing about the class activation maps, or GradCom, or well known as GradCom. First, remember the last previous lessons we have talking about is saliency maps. In the previous lesson, saliency maps answer the questions like which input pixels affected the prediction the most. For example, input image to convolutional neural network, and then it has a prediction like cut, for example. Then we backpropagate to get the gradients of the prediction with respect to every pixel. So that results is saliency map. The output highlights important pixels, and the problem is pixels themselves are not what convolutional neural networks actually understand. So CNNs don't recognize cuts from individual pixels. Instead, CNNs recognize features, not individual pixels. What does CNN actually use? So as an image moves through the convolutional neural networks or convolutional neural layers, early layers learns like edges, corners, textures, and middle layers learn eyes, noses, wheels, windows, and deep layers learn faces, animal bodies, cars, and airplanes. These are represented as feature maps. Instead of asking which pixels mattered, the class activation map, or COM, ask which feature maps mattered. This is a much better question. So, what is feature map again? Every convolutional filter produces one feature map. Example, suppose a layer has 64 filters, then output is 64 feature maps. Each feature map detects a different pattern. Example, feature map 1 detects edges, feature map 2 detects curves, feature map 3 detects eyes, feature map 4 detects fur, and so on. So forth. Which convolutional layer should we use? Every convolutional layer has feature maps, but which one is the best? That's a question. So, we use the last convolutional layer. Why? Early layers only see tiny image regions. They detect edges, textures, simple colors. Those are too primitive. And middle layers, now the receptive field becomes larger. The network sees eyes, ears, noses, wheels. That's much better, but it's still incomplete. And the last convolutional layer sees a very large portion of the image. It can recognize entire cat face, entire dog body, car front, bird wings. These are rich semantic features. That is exactly what we want to visualize. Example from the ResNet 50. So ResNet, its last convolutional layer outputs 2048 feature maps. Each feature map is 7 by 7. So instead of 224 pixels, we now have 2048 7 by 7 maps. Each 7 by 7 location represents a region of the original image. So why are feature maps only 7 by 7? Because after many convolutions, pooling, downsampling, 6, 28, 14 by 14, and now 7 by 7. Now each cell summarizes a large image region. So the main question, now we have 2048 feature maps, but not every feature map is useful. Example, suppose the image is cat. Maybe feature map is 10. Detects whiskers, that's very important. And feature map 732 detects airplane wings, not useful. So we need to know which feature maps contributed the most. How do we measure importance? This is where gradients comes in. Exactly like saliency maps. The lesson says, take the gradient of the class score with respect to every activation and every feature map. Suppose one feature map like having a specific activation and its gradients and just have the gradients. Every activation has one matching gradient. So if we have the activation and gradient, that is 1 to 1. So what does one gradient mean? Suppose activation is 7 and the gradient is 0.4. That means if we slightly increase activation to 7, the class score increases significantly. So it means if we have the large gradient, that is important, and if we have the small gradient, that is not important. But there are 49 gradients. Each feature map is 7 by 7. Means 49 activations and 49 gradients. We don't want 49 numbers, we want one important score. And here's the global average pooling comes in. So GradCam averages all gradients. Example, we have 0.2, 0.3, 0.1, 0.4, 0.5, and then we average it with the total of 0.3. So that becomes the feature map's weights. So that averaging over the height and the width, like dim 1 and 2 in PyTorch, produces one weight per feature map, representing how much that map influences class overall. Now feature map has one weight. Instead of 2048 maps and 49 gradients each, we now have feature map 1 having a weight 0.75, feature map 2 is 0.10, feature map 3 weight is 1.4, and so on. These weights measure importance. Why multiply feature maps by their weights? Suppose feature map A is important because its weight is too large, like 2.5, and the feature B is unimportant because its weight is too small. If we simply added them, both contribute equally. That is wrong. Instead, we multiply the feature map by its weight. Now important maps become stronger, unimportant maps become weaker, exactly what we want. So building the final class activation map, you start with 7 by 7 zeros. Then for every feature map, we added them together. We sum all the weight per weight by feature map. So let's go through 2048 feature maps, multiplying each activation by the map's weight and summing them position by into the new 7 by 7 map. So mathematically, the summation of weight sub I and feature map sub I, after 2004 addition, we obtain one 7 by 7 heat map. And then we perform the ReLU afterward. Some values become positive, others become negative. Positive means this region supports the class, and negative means this region argues against the class. GradCam wants to visualize only evidence for the predicted class. So it applies ReLU and discards negative values. So negative to 0 and positive promotes positive, only supporting regions remain. And then we perform normalization. We normalize current values might be 1355 and 128, and it is hard to display, right? Because it could have the mathematically bias that, yeah. So we normalize it. So the values is ranging from 0 to 1. Now colors are consistent. And why resize? Current heat map is 7 by 7, so the original image is 24 by 24. We need to enlarge. Then interpolation fills the gap smoothly. So instead of large blocky squares, you get continuous color transitions. So, and finally, we overlay. So we add the original image over with the heat map, and then this produces the GradCam. Now we can visually see the cat face, Paul's eyes, instead of background, sky, grass, if those are what the model relied on. And then we use hooks because the feature maps and their gradients are internal tensors inside the network. Hooks lets us to capture them without changing the model architecture. So in the forward hook, we save the feature maps, activations. The backward hook, we save the gradients. So after one forward pass and one backward pass, we have everything we need to build the GradCam. So, and then we use the one hot vector. Suppose a model predicts a cat, dog, bird, and different of those has different class scores. So the one hot vector like 1 0 0. So because the cat is positioned in the first position, that's why we use the 1 in the first place. So it tells the backpropagation computes gradients only for the cat class that focus on explanation on the class of interest. So the entire grad pipeline is from the input image, forward pass, last convolutional layer, and save the feature maps, forward hooks, prediction, and then choose the target class, backward pass, save gradients like backward hooks, average gradients, one weight per feature map, and then we multiply the weight by its feature maps, and sum all weighted feature maps and apply ReLU, normalize, resize it like 7x7 the image size, from the 7x7 to the actual image size, interpolation, overlay on the original image, and then we have the final output, the gradient comp heat map. So the key takeaways here, to summarize, Silency maps explain predictions at the pixel level, but the GradCamp explains prediction at the feature level, using the feature maps instead of raw pixels. The last convolutional layer is chosen because it contains the richest, most semantic features while still preserving special information. Gradient for the chosen class. Global average pooling converts each feature map's gradients into a single important weight. Each feature map is multiplied by its weight, then all weight maps are summed. And ReLU removes regions that oppose the class, leaving only positive evidence. And then the resulting 7x7 map is normalized, resides to the original image size, overlaid as a heat map to show where the model looked when making its prediction.